Welcome back everyone, this is Shivani Garg. In the previous lectures we have studied the methods for solving swing equation, that is modified Euler method and Runge-Kutta method. In this lecture we will be studying the examples on these methods. So let's get started. So we have an example. Consider a system having the following parameters: PM is equal to 3 per unit, R1 PM is equal to 1.2 per unit, R2 PM is equal to 2 per unit, H is equal to 3 per unit, F is equal to 60 Hz, and del T is equal to 0.02 seconds. If P is equal to 1.5 per unit, determine the rotor angle and angular frequency at the end of 0.02 seconds using modified Euler's method. So in this we only have to do one iteration, as it is showing it is asking the values at the end of 0.02 seconds, and step size is also 0.02 seconds. So we have to do only one iteration. So let's start the solution for this example. So initial angle del naught would be equal to sine inverse PS. As we all know, PS is equal to P max sine delta naught. So from this we can calculate del naught is equal to sine inverse PS by M. So we have already given PS is equal to 1.5 and PM is equal to 3. So we can calculate del naught as 0.524 radians, and initial relative angular velocity would be 0 at time t is equal to 0, d del by dt is equal to 0, that is omega naught is equal to 0. Now using equation, we know that d del by dt is equal to omega, and d omega by dt is equal to ps minus pe upon m, which is equal to pi f upon h into ps minus p, as we know the value of h and f, so we can put the value of m in terms of h and f. So we have d del by dt is equal to 62.83 into 1.5 minus 1.2 sine delta. So we use these two equations for solving this example. So in first step, it is to determine derivatives at t is equal to 0. We know that using modified Euler's method, the initial step is to calculate d1 is equal to d del by dt at t is equal to 0, which is equal to omega naught, and since it is given omega naught is 0, so it would be equal to 0, and d2 is equal to d omega by dt, which is equal to 62.83 into 1.5 minus 1.2 sine delta naught. If we put the value of delta naught, we get d2 is equal to 56.547. Therefore the predicted values would be equal to del p is equal to del naught plus d1 del t, and we have calculated the value of d1 del t, and del naught has also been given in the question. So we have del p is equal to 0.524 plus 0 into 0.02. So predicted value of delta would be equal to 0.54. Similarly, we can calculate the predicted value of angular velocity, that is omega p is equal to omega naught plus d2 del t, which is equal to 0 plus 56.547 into 0.02, which is, if we calculate it, it will be equal to 1.13094. Again evaluate derivatives of delta and omega for predicted values. So to calculate the derivatives of predicted value, we have d1 p is equal to d del by dt at predicted values, which is equal to omega p, and we already know the value of omega p is equal to 1.13094, so d1 p is equal to 1.3094. Similarly, we can calculate d2 p is equal to d omega by dt at predicted value, which is equal to 62.83 into 1.5 minus 1.2 sine del p. We put the value of del p in this equation, we get d2 p is equal to 56.547. So therefore the new estimated variables would be del 1 is equal to del naught plus average value of d1 and d1p into del t, that is del 1 is equal to del naught plus d1p by 2 into del t. If we put the values, we have 0.524 plus 0 plus 1.13094 by 2 into 0.02. Therefore del 1 is equal to 0.5353. Similarly, we can calculate omega 1. Omega 1 is equal to omega naught plus d2p by 2 into del t, Z, which is equal to 0 plus 56.547 plus 56.547 by 2 into 0.02. So it comes out to be 1.13094.